Okay, so my name is Leo, and I present our paper named Formally Verified Superblock Scheduling by Symbolic Simulation. So this is a joint work with 5 other people, and here is our GitLab repository URL for more information. So this research is motivated by the need of compiling optimizations that are certified, so without introduced bugs, because indeed, in mainstream compilers, bugs are often introduced in optimization paths. So an alternative solution is to use a formally verified compiler such as CompCert. And in CompCert, we assume that the source program has no undefined behavior. So here, when we talk about undefined behavior, it means any behavior which is not compliant with respect to the standard. So for instance, when writing out of the bound of an array, and in such a case, the compiler might do almost anything, such as prune the branch as dead code or write in another side variable. But in CompCert, we have the formal correctness guarantee that for any source program, if the compiler terminates and give us a target program, then any behavior of the resulting program is also a behavior of the source one. But sometimes when performing compiler optimization, we need to compute complex function, and so verifying the whole function performing the optimization is very complicated. A typical example of this kind is CompCert register allocation, because indeed verifying the whole register allocation algorithm might be an hard task. So a solution is to only verify the result. So we see the register allocator as a black box, and then we only check the result, because checking the result of a given allocation is a much simpler problem. So this is what does Xavier Leroy in CompCert. And we name this technique formally verified defensive programming. And this technique brings modularity to the compiler, because we might change the oracle without the need to rewrite the whole proof, and sometimes without the need to rewrite anything. And it's more efficient because the external oracle that computes the function might use any untrusted library, such as hash consing or complex data structure libraries. And so now we'll see how to apply this method for intra-block optimization. So some optimization are performed inside blocks of code. So a block here is defined by any sequences of instruction with a single entry point and possibly multiple exit points. And to verify our optimization, we must show and prove that the blockstep semantic we introduce, so the blockstep semantic executes the code block by block, simulates the standard small step semantics of CompCert, which executes the code instruction by instruction. Here are some examples of intra-block optimization, such as people, which consist in replacing some instruction sequences, and instruction orderings. So we'll come back on that later. First, a little example, which is simplified, because here we consider a basic block, so with a single exit point. So if we look at 2 basic blocks, B1 and B2, with the following sequences of assignment, one might see that both blocks leads to the same parallel assignment in the end. So in the end of the execution, R1 is equal to 2 times R1 plus R2, and R3 here is equal to R1 plus R2. And we see that the block B1 is preconditioned by the load instruction that may trap on some processors, whereas the precondition of B2 is trivially true. So we can say that B2 simulates B1, but the converse will be false. And always on the same example, if we symbolically execute this block, we will obtain the following. First, a list of terms, which is the precondition. So here, our load instruction. and a finite map from register to terms corresponding to our previously found parallel assignment. Now, a common issue we face when performing symbolic execution of blocks is that even if our symbolic execution is linear, when structurally comparing terms, the comparison might become exponential. And so, to fix this problem, we use constant time pointer equalities instead of structural equalities and hash counting. Thus, two symbolic executions which are equivalent will be bound to the same pointers in the memory, and so the comparison is constant time. Now let's see an example of one of our contributions. So I present people, which is pairing load and store instruction on the ARM 8 backend, because ARM 8 provides specific instructions which are named load pair, which allows us to load two words from the memory in the same instruction. So on the left, we have a source code with in a range two loads with a write after read dependencies. So the pairing must be done forward. So the first load is deleted and the second one is replaced by the pair instruction. And in green, we have the same kind of optimization, but with a read after write dependencies. So here, the replacement is done backward. And to verify such an optimization, the only thing we have to check is the correctness of this rewriting rule, which is executed just before the symbolic simulation. And this rule is performing the opposite transformation. So here, we start from a pair load, and we convert it into two single classic loads. So proving the correctness of this rule is much easier than direct and wall proof on the people algorithm. Now, for some optimization, it's interesting to have larger blocks, such as superblocks, which are allowing side exits. And in that case, the symbolic state is now a binary decision diagram. So on our previous example, if we perform the symbolic simulation only on live register to be more efficient, we saw that B2 simulates B1 if the register R1 is not live at the label L, and B1 simulates B2 under the same condition, plus a precondition on the template operation here that must not trap. And more generally, in the future, we plan to select even larger blocks than superblock by limiting the number of internal join. But when selecting superblock, it's interesting to lengthen them to have more scheduling opportunities. And all methods to lengthen the size of given superblocks are relying on the same strategy, which is code duplication. So we provide as a secondary contribution a verifier, a very simple verifier that allows us to check all of this transformation on the reverse, so the code factorization. And the only need that we require from the oracle is a reverse mapping from the node of the transformed code to the node of the original control flow graph. Here are some examples of this operation. So if we have the following template control flow graph, on the left, we have loop rotation, which consists in replacing a while loop by a do-while by inserting a condition just before. In the middle, we unroll the first iteration, and on the right, we unroll the whole loop body. Now, we'll see some scheduling. So first, a little recall on instruction level parallelism. We can say that there are two types of processor cores. Out-of-order cores that dynamically schedule instruction at runtime, and in-order cores. In-order cores execute the code in the order given in the assembly. And so it's the task of the compiler to find a good order. Usually, in-order cores feature interlocked pipeline, so that means observationally the assembly semantic is purely sequential. So for instance, the processor might sometimes have to wait for an instruction to finish before being able to execute the next one. Here is a tiny example of scheduling. if we have the following pseudo assembly code, and if we assume a single issue 3-stage pipeline with load latencies of 2 cycles, we see, if executing in the given order, that we have to stall before executing the I3 instruction because the R3 register here is not yet ready to be read. But if we invert, if we swap the first and the second instruction, then we can execute I1 while executing I2, and so there is no stall, and we won 1 cycle in the end. Now, how to configure our oracle for such an example? The answer is that our oracle is parameterized by information of the backend. So those information are the instruction latencies and resource constraint vector. Then the oracle gives us a schedule. So here I2, I1, I3. And then we dynamically verify the result by simulation, by checking that they both lead to the same symbolic state. And here it is the case, so our example was correct. I will now present a little more complex example and the global impact of all of our contribution. In this example, we have a sum square function, which is computing the sum of square of each element of a given array. And on the left, there is the assembly code with the loop enrolling applied. So one can see here that the loop enrolling produces 2 very similar loop bodies. And this is due to register name dependencies with the register D1 and D2 here. So to fix such a problem, we provide a method of register renaming path, which is local to Superblocks. And it produces then, after renaming, the following result. So we allocate 2 fresh registers D3 and D4. And this result in a gain of about 30% with respect to the previous code. Now, more globally, we measured our optimization on 3 different cores. And here in the table, optimization are applied incrementally. And we compare them with respect to the mainline version of CompCert. What we can see is that on ARM 8, we are on average 40% better. On the KV3 backend, we are 62% faster. And on RISC-V, only 14%. The lower gain on the RISC-V backend is explained by two main reasons. The first one is that there is no postpass on RISC-V. And the second one is because less work went on the RISC-V backend since it was had to CompCert. So now it will be time for question. I've listed here some question subject. And I conclude with this slide, which is summarizing our current and future work. So my PhD thesis, which is on block simulation modulo symbolic invariant. Such simulation with symbolic invariant should enable us the verification of global inter-block optimization, so such as lazy code motion or even strength reduction. One other challenge which is left as future work for now, is to integrate an efficient and, of course, verified alias analysis in CompCert within the symbolic execution. So thank you very much.
So I don't see any questions.
You have questions locally? Yes. Just
Hi, thanks for the talk. I'm curious, do you have a sense of how often your optimizer spits out cases that your symbolic executor does not verify is correct? Like, is it guaranteed that the symbolic executor will always, I guess it's not guaranteed, but does it generally always result in checking, in saying that your optimizations are correct, or how conservative is it in that sense?
Yes. In general, the solution is to test the oracle by running a lot of tests and benchmark. So to do this, we rely on commonly used compiler benchmark suites and large and complex application. But sometimes it happens that our verifier rejects the result. For instance, if the oracle is trying to perform something too complicated to be verified by the cock checker, and then we try to fix that and to adapt. But we can't have the guarantee that the verifier will never fail and abort the compilation, of course.
More questions here, locally? No? Benjamin, do you have online questions?
Yeah, I don't see any more online, but I can ask a question. So on your previous slide, you had a note, I guess, prompting us for more questions about the trusted code base, I believe. In particular, there's this question about the trusted code base of CompCert. Do you want to expound a little bit more on that?
Yes, of course. Here is a slide which is summarizing which are the main part of the CompCert trusted computing base. I think it's important to take time to look at this slide because often we may think that using external oracle or external functions that are axiomatized in coq and then verified by a checker might be a problem for the trust computing base. But in fact, in such a huge project as CompCert is, there is a lot of parts that may present problem for the correctness. And in particular, every OCaml external part, such as the pretty printer here, in which some bugs have been found in the previous months and year. So those bugs are bugs which are bugs where the pretty printer assumes things that are not correct with respect to the assembly semantic described in CompCert, or when sometimes the assembly semantics described in CompCert is not exactly the semantics of the target instruction set architecture. I hope this answers the question.
Yeah, thank you. So we have a question from Zhang Xiao on the Q&A chat. Zhang asks, how hard would it be to extend this approach to support inter-procedural optimization?
I'm not sure to answer. Maybe, is it possible that one of the other contributors answer the question?
Yes, if they're online.
On the platform?
They can raise their hand. The student volunteers can bring them on the stage.